So the next section, looking at the various types of equipment, I'll start with the probes that we have. And I say probes, but there's also 3 cables shown here, the cable that connects the probe to the tester. So probes can come in all kinds of different shapes and sizes. Often you'll hear them referred to as coils. However, a given probe, more often than not, a given probe actually contains more than one coil in it. There are some probes that do only contain a single coil, but many contain multiple coils. And those can be for different reasons. They can be used simultaneously or they can be used at different times. That dual current probe I was talking about, high frequency, low frequency, certain coils lend themselves to certain frequencies better than others. So oftentimes when you have a dual frequency probe that's bouncing back and forth, it's not using the same coil to shoot both frequencies. It does one coil for high frequency, typically a smaller coil, and then a bigger coil for low frequency. And it keeps bouncing back and forth between the two of them in a single probe, okay, single package. So they come in many shapes, sizes, and configurations, and you can even get custom design ones. If you have a specific application you're going to be doing, say, a lot of, or that's in a very critical area where you got to make sure whoever's doing it doesn't screw up, you can create custom fixtures and custom probes in order to facilitate those kind of inspections. So the first type, these are called some standard shapes we have are flat pencil bobbin. So again, the custom shapes, one of the most common custom probes you'll see is a wheel bead profile. It's designed to go in the wheel bead area of a wheel rim. When a wheel's overhauled and new tires put on, you run the probe around the bead seat to make sure you're not getting a crack in that area. That's the weak point on the wheel. And the probes shown here are actually spring-loaded. It's a flat face. We have these. You're going to use some of these, this style right here on the right with the slightly smaller. You can see just got 2 different size coils inside of them. That help to keep the probe in contact. Remember I said very small movements of the probe in relation to the surface can cause false indications on your display. And so by having a spring-loaded probe like this with a real wide base, it helps to keep it nice and solid on there. So the arrows here are pointing to the surface or the face of the probe, now, or the face of the coil. Now the coils behind there, they do put what's called a wear plate on there, because obviously running a coil of wire directly over a part probably wouldn't last very long. And so they typically have some kind of a wear plate on there, whether it's some of them are plastic, some of them actually, it can be a non-conductive, it can be like an aluminum, but most of the time it's like a phenolic or a plastic, something like that. The other part is we can create probes that have different materials or different features around them to help contain or direct where the magnetic fields and where the eddy currents are forming. And that's done with things called shielding. So shielded probes, they're going to help to control the spread of eddy currents to try to concentrate them more directly under the probe. And that's especially important if you're going to be putting the probe near features or near areas of the part where the metal does get the geometry changes or something like that, where you don't want that to affect your ability to see what you're looking for. So it can improve sensitivity, reduce something called edge effect. But to add a shield makes the probe larger, physically larger, and so it may not be able to fit in the same tight spaces. So probes come in smaller diameters, larger diameters. There's even probes that are not round, they're square or other oblong or weird shapes for specific applications, which create really funky magnetic fields and stuff. But for aviation, a lot of times we use fairly small diameter probes because we're looking for surface cracks. And so these are operated at those high frequencies, those hundreds of kilohertz or even into the megahertz range. It allows us to find these small surface flaws, as well as have good access to tight areas. They also reduce something called edge effect. If the probe is smaller and you get near an edge, right, you can get closer to an edge without part of the probe going off the edge of the part. And edge effect is, again, if you're taking a probe across a piece of material and you get to the edge, right, the material in front of the face of the probe is going to be changing. You'll get an indication because of that. You'll have to show, one of the examples you'll have to show on every one of your tests is the edge effect with your given probe and tester setup. So because sometimes edge effect can look like a flaw. So you want to make sure that is it because your probe got too close to the edge, or is it because your probe found an actual flaw? Okay. But a small probe, only does a small area, and so it's relatively slow coverage. Right? If we have to scan the entire fuselage, and our probe is the size of the tip of my pen, it's going to take a really long time to scan that entire surface. Right? Something like that might be used in very specific locations, like you go around each rivet head versus having to scan the whole surface. Right? There are probes designed for surface scanning. Larger diameter probes are your higher depth of penetration, lower frequency probes. And they're not going to find the small flaws, but they're better for finding that subsurface, those subsurface indications. They also can cover a larger area faster just because it's a bigger probe that you're moving around on a given part. Here's an example, a couple examples of those specialty shapes. So here is a probe that's designed to fit. What do you think this is? What is this probe in right here? Does that look familiar to anybody? What's that? A turbine. I heard turbine hub, turbine blade, right? So this is the hub, the disc, right? This one's, it could be turbine, it could be compressor, it could be fan, right? It's the disc that blades go in. Who knows what kind of blade route this is? This is a bulb style. You have to know those on your written tests. So this has bulb style, blade roots, and they're checking for, cracks probably. You don't want a crack propagating from one bulb area to the next, right? Those thinner points there. And so you have probably a plastic profile designed to fit in there. And something like this could have a coil on each side, or it could have a coil on one side where you'd have to run it through one way, flip it around, run it through the other way to check the other side. Or it could have a coil that kind of follows the profile. It could be some kind of an odd shaped coil that kind of follows that profile. There's all different ways they can run the wires inside of there where it'll induce the field for that. Below is something called an array probe. And array probes have multiple coils. They come in all kinds of arrangements. And these ones, some of them are even like this one right here on the right, or this end on here, that's the plug for it. But the end here, this actually is like a pad on the bottom of it. So it's actually kind of a squishy surface where you can push it against an irregular surface. And these can scan a wider area. So if you're trying to get, like map corrosion on a surface, you would run, would run at a low frequency. For example, you run it across the outside surface and it would map. It could even do like a 3D map of what the corrosion or what the roughness looks like on the back side of that material. I'll show a video of this a little bit later. On the top here is a hole probe. So these come in different diameters. You can see they look a lot like your little ball gauges you've used in overhaul class and stuff like that. And so these slide into, you'll have a hole probe of a specific diameter that'll slide into one of those. So you're going to do this. We have a hole probe you're going to use as part of your lab. They can be used manually. You'll use them manually. What they're showing here is a hole probe mounted in like a little motor that spins it around. So you don't even have to sit there and twist it yourself. You just plunk it in the holes while it's going. An encircling probe, we have some of these. You won't use them in the lab, but if you want to do a self-design that uses a rod or something that fits inside of one of our encircling probes. In this case, now instead of the coil being put in close proximities, you actually put the part through the center of the coil. Right? Because the center, if you put something through the center, okay, this goes back to systems class. What did we talk about where we changed, what device did we use where we changed the material that was in the center of a coil? Remember? LVDTs and RVDTs, right? This works kind of on that same concept. You run this rod through the middle. As long as the rod is homogeneous, the inductive reactance and the impedance of the coil isn't going to change. But if you have some kind of a flaw or discontinuity or a crack, if that passes through the coil, you're going to get that change in impedance that your tester is going to pick up. And you'll be able to see that. So that's called an encircling probe. We can have bobbin style probes designed to go through cylindrical, like tubes and pipes and things like that. This one, these examples have multiple coils. This is what I'm talking about, where you can have multiple coils. So, they show a simple one here with 2 coils, something like this. There's 2 coils that wrap around. They go circumferential on here, and then you have a bunch of coils that are, pancake orientation to the surface. So they're going to create magnetic fields in 2 different directions to possibly find flaws that run different directions. Or these are big coils, these are little coils. These are finding cracks on the inside of the tube. These are looking at corrosion on the outside of the tube. Say you have a pipe that runs underground, and you want to make sure that the inside is in good condition and that you aren't getting, particularly like steel pipes used in gas and oil, that there isn't corrosion forming from the wet soil being around the outside of the pipe without having to dig the entire pipe up and inspect it manually. They may use something like this. The bottom one here, pencil type probes, they can come in all different configurations. So we have probes that are similar to these, where it's just a little tiny, one tiny little coil on the tip. And then we've got these spring roller. These are considered a pencil probe, even though they don't look as pencil-like. It's a small coil that is placed on the surface. Those just happen to have that spring device in there that helps it maintain contact. So those are the different configurations of probes. The way the probes are operated is also plays a role. So there's different probe types. So modes of operation, the 4 most common, well, the 3 common ones are absolute, differential, and reflection. And then a hybrid is a combination of any of these 2 or more, or 3. So our test equipment, though, the big key is certain probes are designed to work in certain modes. You can set the mode on your test equipment, and if yours is not automatic, which ours aren't, ours are manual, you have to match your setting to match the type of probe you're using. You get some really weird results, or it's really, really hard to get it to work if you have it set for the wrong probe type. So you have to pay attention. What is the probe type? Now with a hybrid probe, which a lot of our probes are hybrid, they're going to primarily they're going to act more like an absolute. It might be a combination, but you may have to set it. You'll use the reflection setting, or you'll use the differential setting. Even though it may have you might set it on the reflection setting, but it may have a certain amount of behavior like a differential probe. Okay, so manual, most are manual. Some of the real high-end stuff coming out in the last few years is automatic, can automatically detect basically where the probe and the device can talk to each other. And then the probe type, you have things like the number of coils, the number of turns of wire, how big they are, and then whether your coils are powered or not. Sometimes you can run power to the coils. Sometimes there's passive coils that are doing more listening. Sometimes there's coils that are more amplified than others, right? There's all kinds of configurations and things that can be done inside to try to get different results or to try to see different things. So I'm going to go ahead and stop there. Oops.